as we continue our discussion of thermochemistry, we've got to talk about state functions. State functions are determined by the state of the system regardless of how the condition was achieved. Yes, I just read that to you, but it says, I don't care how you got to the top of that mountain, you're still at the top of that mountain. Altitude is a state function. So start here, end there, whether you take this blue path that's more straightforward and steep, or this windy path that's red and curvy and less steep all along the way, you end up at the top of the mountain regardless. So altitude is a state function. It doesn't matter how you got there, you're ending at the same state regardless. Enthalpy is a state function. It doesn't matter how you get there, you end in the same place. You can end in the same place. Okay, so here are 3 enthalpy values for solid water, also known as ice, or liquid water, or gaseous water, also known as steam. If I want to convert ice into liquid water, is that an endothermic or exothermic process? It's endo, because you have to put in 6 kilojoules per mole of water to turn solid ice into liquid water. It's an endothermic reaction. That arrow is pointed up, and any time on an enthalpy plot when the arrow is pointed up, that's endothermic. So this is our reactants shelf and our products shelf. That's what I'm defining. If I wanted to turn liquid water into gaseous water, if I wanted to turn liquid water into steam, that would become my reactant shelf, and this is my product shelf. I'm going to put in more energy. I put in actually 44 kilojoules per mole of energy, of enthalpy, has to be put in to turn liquid into steam, so to boil water. There's my 2 equations for that. Solid going to liquid, liquid going to gas. What about if I want to turn solid into gas? Do I stop at the liquid train on the way? Possibly, probably. Can you turn solid directly into gas? Well, we're not going there. But solid, going through a liquid first, then going to a gas, it doesn't matter how you get there. When you're going from solid to a gas, the total enthalpy input will be 50 kilojoules per mole, because it takes 44 to go from liquid to gas and 6 to go from solid to liquid. So 50 is what's required to get it from solid to gas. That's a state function. It doesn't matter how many other steps or part steps you went through in the process, you end up at the same place. So, enthalpies. If we're sitting on this liquid water shelf down here, another transition we could do is break that down into H plus and OH minus ions. That is a thing that happens in water. The enthalpy input for that is endothermic. How do I know that? Because this shelf is higher than that shelf. The energy input I can look up in a table says that requires 56.2 kilojoules per mole. I could do the same thing if I talked about coming from solid water, going up to aqueous ions of H plus and OH minus. I would add this number and that number together, and that would tell me how much energy the whole transition from solid to aqueous ions would be. That's not where I'm going here, so I'm going to delete that and say, here's my gaseous stuff, and how do I know that that shelf of gases should be lower than this one? Because I know that my liquid required 44 kilojoules per mole from the last slide. I know that. I know that it requires 44 kilojoules per mole to get up here. So it must mean aqueous ions are higher enthalpy values relative to gas, because I know this enthalpy input is greater than that enthalpy input. Yeah? Does that make sense? I hope. I'm talking to an empty room, I know, but if I wanted to go from gas to solid, so I'm saying the gas is my reactants shelf and the solid is my product shelf, number one thing you can tell me is that endothermic or exothermic? It's exothermic, and it's going to release 50 kilojoules per mole. So something that's often confusing for students in the very beginning, especially when I say it releases 50 kilojoules per mole, the word releases implies the negative, or I can say the enthalpy change is negative 50 kilojoules per mole. So saying it releases 50, I don't say it releases negative 50. That's a double negative, and double negatives ain't no good. Releasing 50 implies it's negative 50, or the change is negative 50. Yeah, okay. So gas to solid releases 50 kilojoules per mole of energy. Some of what we will work on in this activity is plotting enthalpy plots, and some of what you will need to know is which shelf should be highest and which shelf should be lowest, etc. One big point here is absolute enthalpy values are not known. They're only measured relative to each other. So I cannot say that this has an absolute enthalpy of something. I can only measure the change when I turn this liquid into solid, or the change when I turn this liquid into gas, or the change when I turn this liquid into these aqueous ions. I can only measure changes. I cannot measure absolute values. So because I can only measure changes, we have the freedom to define a reference point, the freedom to define what is zero, the freedom to say, this is what I'm defining as zero, and I will reference all other enthalpy values to this 0 point. So there are two major definitions for what reference points we will use. The chem-activity book that we follow defines atoms in their gaseous state as 0 kilojoules of enthalpy. So if this plot is all about water, if you broke liquid water down into single gaseous atoms, I'm not saying these are stable things, these are not stable things, single gaseous hydrogen atom and a single gaseous oxygen atom and another single gaseous hydrogen atom, 2 moles of single atoms of hydrogen as a gas in the gaseous state, and 1 mole of oxygen as a single atom in the gaseous state, the chem-activity book defines that point as 0. So because they're defining that as 0, anytime you combine atoms to make things, that is always going to be an exothermic transition. Anytime you combine to go down, that is always going to be an exothermic transition. Endothermic are when my arrows point northward, like this orange one over here. That's endothermic. That's endothermic. Anytime I have an arrow pointing north on an enthalpy plot, that's an endothermic transition. Energy is required to make that transition. Anytime I have an arrow pointing southward, that's an exothermic. So anytime you have atoms that are coming together to make new bonds, making new bonds is actually an exothermic transition. Breaking bonds is endothermic. Making bonds is exothermic. Making bonds releases energy. Breaking bonds requires energy. Good thing this is recorded. You can rewind that and hear me say it again and again and again. It's probably something you need to hear me say again and again and again, unfortunately. Yeah, I drew that plot before I started drawing all these. Let me erase all this stuff. What does it say? The enthalpy of atom combination. Sorry, I meant to point that out. The enthalpy of atom combination is taking these atoms, combining them to make, apparently I wanted to talk about gaseous water. So when I combine these atoms to make gaseous water, how much energy is released? I look in the back appendix of my chem-activity book, and I see that that releases 926.3 kilojoules of energy to bring that together and make gaseous water. Note in the back of that book where you're referencing enthalpy values, the state of the thing you're referencing is very important. Liquid water will release more energy when you create liquid water out of gaseous atoms. It will release more energy than 926 kilojoules. It would release 926.3 plus 44 kilojoules to create liquid water instead. I did say plus, but I mean plus negative, so it would be like negative 970, if I did that math correctly, 970.3. Let's hope I did that math right. I don't know. So I said enthalpies are not known absolutely. They're only correct relative to each other. You're measuring changes, you're not measuring absolute values. So we have to define some sort of reference point. So I already talked about that, but let me define what our two most common reference points are. So the back of our chem activity book uses atom combination tables. Combination. I got ahead of myself and spelled badly. Atom combination, the back of the chem activity book. Enthalpy of formation in the back of our textbook, in the back of most textbooks. So because enthalpy is a state function, it doesn't matter how you get there, you're going to end up at the same spot regardless of the transition. Atom combination defines zero enthalpies as atoms, single atoms in their gaseous state. Formation enthalpy tables defines zero enthalpy values as, I'm kind of saying this definition backwards, but we're going with it now. Defines things as elements in their standard state as zero. So what the heck does that mean? It means in an atom combination table, you will find something like carbon as gas equals 0 kilojoules enthalpy. Iodine as gas will equal 0 kilojoules of enthalpy. Sulfur as a gas will equal 0 kilojoules of enthalpy. In a formation table, carbon as a solid, carbon as a solid because that's its standard state, or iodine as a diatomic solid, or sulfur as a solid, those values will be defined as 0 for formation enthalpy tables. Does it matter where you define as 0? Not at all. Enthalpy is a state function. What matters is that if you're using formation enthalpies to calculate a delta H for some reaction, you use all formation enthalpies. If you're using atom combination enthalpies to calculate delta H for some reaction, you use all atom combination enthalpies. You cannot mix and mingle because they're only correct relative to each other. If I cross one of these values and one of those values together, I am not getting a correct enthalpy value out of that, out of the combination of those two. So what that leads to, one thing I want to point out, and then we're moving along, because single elements in their gaseous state are 0 in atom combination enthalpy, all values in the table are negative. Because you're combining atoms to make bonds, like when we made water a moment ago, you're combining atoms to make bonds. And anytime you're combining atoms to make bonds, that's going to be an exothermic process. So the definition is you're going to have atoms, and you're always going to make a molecule. You're usually going to make a molecule. Molecule. And that's an exothermic process. But in formation enthalpy tables, you will have positive, negative values for your enthalpies. Both types of values will be there. So some enthalpies in the back of the book are positive enthalpies. Some enthalpies in the back of the book are negative enthalpies. But in the back of the chem activity book, they are all negative because they are atom combination. It just means your 0 reference point is different, but your relative numbers, your delta H of the reaction overall, should not be different. And the process for calculating delta H of the reaction overall is not different. We can talk about it as final minus initial. We can talk about it as products minus reactants. It's the same thing if you're using atom combination tables and you're calculating delta H of reactions, final minus initial, products minus reactants. If you are talking about formation enthalpies, delta H of a reaction, final minus initial, product minus reactants, done. It does not matter. I've spent a long time talking about this, but yeah. Let's talk about an enthalpy plot specifically. If we are using atom combination tables from the back of our chem activity book, how would we make a plot that helps us determine delta H of the reaction for this given reaction? Well, first of all, my 0 point is atoms in their standard state. That is defined as 0. So I'm going to break all this down. How many hydrogen atoms on the left-hand side? 4. How many oxygen atoms on the left-hand side? 4. So because I know that's what's going to combine together in this whole system, I define that as 0, and I'm going to start my enthalpy plot with that shelf. And then I'm going to visit Appendix 3 in the back of the textbook, and I'm going to look up the enthalpy value of H2O2 as a liquid. And back in the back of the book, I find H2O2 as a liquid as negative 1121.42 kilojoules per mole. So I'm reacting 2 moles of this stuff. So if I draw a shelf for my 2 moles of H2O2, I'm going to put that shelf at negative 2242, I can't, 2242.84. That's a 4 kilojoules. So that's on my y-axis over there. And how did I get that? 2 times the number from the back of the book tells me the value of the y-axis where my reactants shelf should be. Then I visit the back of the book and I look up water as a liquid and oxygen as a gas. I got negative 498.34 kilojoules per mole. And I got negative 970.30 kilojoules per mole for water. Water needs to be multiplied by 2, and then those values need to be summed together. So when I say delta H reaction is final minus initial, or products minus reactants, it's the sum of the enthalpies of the products multiplied by their coefficients minus the sum of the enthalpies of the reactants multiplied by their coefficients. So I'm taking oxygen, multiplying it by 1, and adding it to water multiplied by 2. My total enthalpy of my products is negative 2438.94 kilojoules. So what that actually tells me is that shelf needs to be at 2438.94. On that shelf, I've got 2 moles of water, liquid, and 1 mole of O2 gas. So for this whole transition, if I think about it in the atom combination way, I'm going to rip this thing into pieces, and I'm going to put in positive 2242.84 kilojoules to do that. And then once it's in these gaseous atoms state, they will recombine and release 2438.94 kilojoules. So it doesn't matter that I ripped it all the way into atoms. It doesn't matter if I ripped it into single elements in their, elements in their standard state. It matters that I started here, that's my reactant shelf, and I ended here, that's my product shelf. The overall transition is final minus initial. 2438.94 minus 2242.84. Final minus initial is my delta H overall. So the value of my little orangish arrow right there should be negative 196.1 kilojoules. That's enthalpy plots. One little thing I want to say to make getting started on our chem activity a little less cumbersome. Some of the first few questions are about this sort of treating protons as a bare nucleus, a bare nuclei. It talks about the potential energy, the Coulombic potential energy equation, which is this thing. So you have 2 points out in space. Those 2 points that are protons out in space repel each other. This arrow is a repulsion force because those charges are the same, they repel each other. If you put an electron in the middle of those 2 points, this proton will experience an attraction force. Whoops, clicked the wrong one. This one will experience an attraction force, and this one will also experience an attraction force. So there's one repulsion force between these 2 points, but there are 2 attractive forces. Repulsive forces are positive, attractive forces are negative, and there's some energy minimum where everybody is a fantastic distance, everybody is pleased, your energy is minimized when you're bringing all this stuff together. One of the big points I want to make is if you rip that thing from this energy minimum, rip it into faraway points, that's an endothermic process. You must put energy in to rip those things away. But if they come together, right now, over me, they come together, they release energy when they do that. That is an exothermic transition to go down. I think I've talked enough. I'm done. Let's move on.